Welcome to Lecture 16. Here we are continuing our study of trigonometric equations. So let's start with question number 1. We have the equation 2 root 3 sine of x over 2 is equal to 3, and we need to solve this on the interval from 0 to 2 pi. So the first thing we want to do is we want to get the trig function by itself. That would mean dividing both sides by 2 root 3. And here would be the result. So next, of course, we need to rationalize the denominator. So now we have a sine value equal to the square root of 3 over 2. We are dealing with radians, so now we want to draw our unit circle. And then on the y-axis, square root of 3 over 2 is about this far up. So we have a dot here over on the right, dot here over on the left. This first dot corresponds to pi thirds, and the second one corresponds to 2 pi thirds. So far this is not any different from what we did in the previous lecture. What's different is the fact that inside the trig function, we no longer have a plain old x, or a theta. We have x over 2. So what we want to say then is that this angle right here would need to be pi thirds or 2 pi thirds. So now we need to set x over 2 equal to these two values. So when we set x over 2 equal to pi thirds, and then multiply both sides by 2, that means that x is equal to 2 pi thirds. And then we can do the same procedure again over here with setting x over 2 equal to 2 pi thirds. Put a semicolon in between these. You don't want to have a string of equal signs. Be very careful that you do not have a string of equal signs unless your string of equal signs represents values that are actually equal. This string of equal signs is okay. We don't want to do a string of equal signs right here because we're switching from x over 2 to x. So a comma or arrows, something like that would be more appropriate. So as we were saying, we end up with the value of 4 pi thirds. Now we want to ask ourselves, are these values both between 0 and 2 pi? Because if this second value, and this would be very possible, if this second value had been multiplied by 2 and had been giving you a result that was beyond 2 pi, then you would want to reject it. But in this particular case, we see that 2 pi thirds and 4 pi thirds are, in fact, the solutions. Okay, so let's go down now to question 2. We'll go through this one a lot faster. First, you want to just consolidate. You have a sign over here on the left and a sign over here on the right, so move the one on the right over to the left, and what's the result? So once you consolidate the 2 sine x over 2's, they're going to both be on the left. That would make 2 sine of x over 2, and then divide both sides by 2. So the sine of x over 2 is equal to square root of 2 over 2 on the unit circle. Those values are at pi fourths and 3 pi fourths. And as in the previous problem, you will then set x over 2 equal to each of these values, multiply by 2. If you multiply this one by 2, you end up with pi halves. Multiply this one by 2, you end up with 3 pi halves. So those are the answers that we would expect. And there you go. Okay, so next I want to look at number 40 from the textbook. So here's number 40 from page 279. We have 2 square root 3 of cosine x over 2 is equal to negative 3. So what we want to do first is divide both sides by 2 root 3. The result over here is going to be, of course, a number that needs to have its denominator rationalized. And so the result is that cosine of x over 2 is equal to negative root 3 over 2. So next we draw our unit circle. And on the x-axis, going back to negative root 3 over 2, we have 2 locations. we have 5 pi sixths and 7 pi sixths, where the cosine is equal to negative root 3 over 2. So then we want to set x over 2 equal to 5 pi sixths, and then also set it equal to 7 pi sixths. So that is the value inside of the trig function would need to equal 5 pi sixths or 7 pi sixths. And now we multiply by 2. So x is equal to 5 pi thirds. X is equal to 7 pi thirds. Now, had the problem said pick the numbers between 0 and 2 pi only, then you would need to reject this number because this number is greater than 2 pi, right? 7 thirds is 2 and 1/3. So that would be a different set of directions, though, because if we look at the book, it says x is in radians, and we need all exact solutions. So we are going to be adding 2 pi k, and by adding 2 pi k to each of these solutions, then we do in fact have all the solutions that we were looking for. So it's no, it's not. I just made an error. And I'm glad I made this error so that you can learn from it. Okay, this is what you need to do, because what I just did is wrong. You need to add the 2 pi k right here. See, common mistakes are good to make in front of other people so that they don't have to make the same common mistakes. When you multiply both sides by 2, we end up down here with a 4 pi k. Okay, so we don't automatically add 2 pi k to the final answer. We actually want to add the 2 pi k up here, because this is where we're going to be going around. Every 2 pi k, we get back to 5 pi sixths. Then, once you multiply by 2, both the 5 pi sixths gets multiplied by 2 and the 2 pi k gets multiplied by 2. So now this is your final answer. So make sure that you put the 2 pi k up with the initial solution before you get to your final solution. This would be the unadjusted solution. And the unadjusted solution will have the 2 pi k. All right, back to my open math. And we see we are at exact solutions on the interval of 2 pi. But here we have something a little interesting going on. We have a sine of 2 theta. So, given that we have a sine of 2 theta and we have a cosine of theta, and these are not the same functions, we already know from the previous lesson that we don't want to solve a trig function unless we have all the same function, or unless somehow we can factor out functions in a way that we can get a function isolated by itself in a factor. So since we can't do that here, what we want to do is we want to replace the sine of 2 theta. Using the back of the book, we see that the sine of 2 theta is 2 sine theta cos theta. So we want to rewrite this. So now we have replaced sine of 2 theta with 2 sine theta cos theta. Now you want to subtract the cos theta from both sides. And then you want to factor out the cosine of theta. So then you have 2 separate factors, and each one can individually be set equal to 0. And then, of course, we do not have the same, we don't have the problem with 2 different trig functions within the same factor. So when you set cosine of theta equal to 0, you'll get one solution. Set sine of theta, 2 sine theta minus 1 equal to 0, you'll get another solution. So, of course, cosine of theta is equal to 0 is already fully simplified. Set 2 sine theta minus 1 equal to 0, and you can rewrite that as sine theta is equal to 1/2. And then we draw our unit circle, and we identify the locations on the circle where cosine is equal to 0, or the sine is equal to 1/2. So the cosine is equal to 0 up at the top at pi halves, down at the bottom at 3 pi halves. The sine value is 1/2 at pi sixths and 5 pi 6. Now this technique right here is the same technique you'll use down here. Notice in question number 4 we again have a sine of 2 times an angle, so use the exact same substitution. Of course, in this problem we have a w and not a theta, so it would be 2 sine w cosine w, but you replace this part of the equation and you still have the 8 out in front. 8 times 2 is 16. Make sure you pay attention to that. And then you have a cosine in both terms, so you can factor it out. So use the exact same technique for question 4. And look, there's a help video in case that didn't make sense. All right, so back to here, we've got pi 6, pi halves, 5 pi 6, and 3 pi halves. So let's see these listed out. Ta-da, there they are. Now when we get down here to question number 5, we have a cosine of 2 theta, and remember that with cosine of 2 theta, you have multiple choices as to what substitution you can make. You can make a substitution that involves both cosine squared and sine squared, one that involves just cosine squared, and one that involves just sine squared. Given that the other part of this equation is a cosine squared, you would want to pick for your substitution the formula that also uses cosine squared. So we'll start by replacing cosine of 2 theta. Let me do this one on the board. Here's question 5. So what I was saying is you want to replace cosine of 2 theta with the formula for cosine 2 theta right here from the back of the book that involves another cosine squared. So it would be 2 cosine squared minus 1. In this case, 2 cosine squared theta minus 1. Always remember that you need to attach an angle to every trig function. In the equations, of course, the angle will be a variable, same as with proofs. In other contexts, you might see an actual number. But the variables are very commonly dropped by students, so don't drop them. Okay, so now we just need to clean this up a bit. We've got a 12 cosine squared, a 6 cosine squared, so that nets us a 6 cosine squared. This is a negative 6, and a negative 5 gives us a positive 1. So now the cosine squared of theta is equal to 1 over 6. Okay, so far so good. Now we're going to take the square root of both sides. Remember that when you take the square root of both sides, you need to add that plus or minus. That would be the square root property. And then we're going to multiply by root 6 over root 6 to rationalize this denominator. So we have that the cosine of theta is equal to plus or minus root 6 over 6. So drawing the unit circle, we've got a notch on the positive axis and the negative axis. We've got some sort of value in each quadrant. Now one thing you want to note is the angle that's being formed by these dots against the y-axis. These are all going to be congruent angles, right? So once you find one of these dots using a cosine inverse function, you can find the other ones pretty quickly. So let's go ahead and pull up a calculator here on the screen. Okay, so I want to take the cosine inverse. Notice that I am in radians of the square root of 6. I'm going to end the parentheses there before I do my division. Make sure that you are paying attention to your use of parentheses. A lot of mistakes are made that way. Okay, so we have arc cosine, which is the same as cosine inverse of square root of 6 divided by 6. And the result is 1.15. And it's nice that there is a 0. I don't know what we're rounding to. I guess I should check that. Okay, let me go and check that real quick. 3 decimal places. Ooh, glad I looked. Okay, so for the sake of what I'm doing right now, I'm going to go ahead and go out more than 3 decimal places because I don't know if I might pick up a rounding error somewhere. All right, let's go back to the board. So I've written 1.15026. This angle right here is going to be congruent with this angle right here. So this value right here I can get using arc cosine, or I could just take pi and from pi subtract 1.15026. So let's do it both ways so you can see that. Back to the scientific calculator. If you take the arc cosine, whoops, I do not want to multiply that. Clear, all clear. Okay, I could have just squeezed in a negative somewhere, I'm sure. Arc cosine of negative, can I do that? Maybe not. Square root of 6, negative. Square root of 6, now negative. Give me a negative. I'm sorry, I'm new to this one. I apologize. Square root, I finally just used my keyboard, wasn't that a good idea? Divided by 6. Okay, that is 1.99133. And then I said alternatively, what we could do is we could take pi and from pi subtract 1.15026, and oh look, we get the same thing, 1.99133, right? So this value right here again, this 1.99133, we can either get using arc cosine on the negative root 6 over 6, or we can do pi minus this number since these two angles are congruent. So getting down to these next ones, how do we get this one down here? Well, this one right here is going to be, here's pi, remember, so this would be pi plus 1.15026, and then this one over here, here's 2 pi, and working back from 2 pi, can you see the bottom of this right here? Working backwards, this would be 2 pi minus 1.15026. So let's get those values really quick. Okay, so I want to now do pi plus 1.15026, and I get 4.29185. And then I can also do, all clear, 2 pi. Oh, look, it's keeping record of previous things I've done. How cool is that? 2 pi minus 1.15026. And I get 5.1329. That's good enough. Okay, so what I want to do now is go back to my open math where I'm going to look at all of the answers. So I have 1.15, this is actually 1.150, 1.991, 4.292, and 5.133. Those are all the values from the board, but to rounded to 3 decimal places. So this one rounded 1.150. It didn't write the 0 out, but the 0 would be included technically. Here this is 1.991. This one, 4.291 got rounded up to 4.292, right? And then this one right here, 5.132 got rounded up to 5.133. So make sure your rounding is on track. It's better to round at the end and drag out your decimal places a little further during the problem so that MyOpenMath doesn't fault you for being 0.001 off because of a rounding error that you accumulate. Okay, back to MyOpenMath. This one right here just wants the two smallest values. And the fact that it has a 3x here, we don't have a 3x equation, right? Now, of course, you could come up with something creative like x plus 2x, but why would you do that when you already have one trig function? So how are we going to do a problem like this? Well, tell you what, you've got 2 videos. You can watch those. I will do a different one. Both of these are going to be the same type of problems, except this one, remember A has to be smaller than B when you enter these. In case you wanted to practice that particular problem, those are the answers. And then down here it's going to be for the smallest 3 positive solutions. So that one's a little harder, so I will go ahead and do question 7 on the board. Okay, so here we are, and we want to start by dividing by 8. Of course, 6 over 8 is 3/4. Then we are finished isolating the trig function, so now we just need to draw the unit circle and have some dots here. Now 3/4 is not a value on the unit circle, so we're going to need to use the scientific calculator to get ourselves an approximation for the first dot. So let's go back to arc cosine, all clear. Arc cosine of 3/4, or I'll just type in 0.75. Okay, and the result is 0.7227. 0.7227. I am assuming we're still in radians. Assuming's not a good idea, so let me look. It doesn't say. Those answers look like radians. Okay, so we're in radians, because I said so. Okay, so back here is your first answer. And then to get this other answer right here, and I would say plus 2 pi k. And to get your other answer back here, since this angle right here is congruent with this angle right here, this one is going to be 2 pi minus 0.7227. So I'll go ahead and go back to my scientific calculator. And actually, I'll just subtract 2 pi from it. No, not in parentheses. Close the parentheses. No, close the parentheses. There we go. Minus 2 pi. This will be the opposite of my answer, right? Can I handle that? Okay, so now I could push this button, or I could do it in my head. I needed a positive value, which is 5.56. This is more accurate than me using a rounded value, 0.451 ... plus 2 pi k. All right, back to the board. Ta-da, here we are. Now, these are the values where if you plug them into cosine, you would get a result of 3/4. But we actually have a 3x here, right? So what that means is I then need to take 3x and set 3x equal to each of these values. And then I divide everything by 3. So if I divide this first value by 3, back to the scientific calculator. Clear. Okay, so if I want to be technical, I could do the arc cosine of 0.75 and then divide that value by 3 to avoid a rounding error. And I get 0.2409. 4 decimal places is good. Plus, going back to the board, remember we're dividing by 3, not only the 0.7227, but also the 2 pi k. So we divide 2 pi k by 3, and we get 2 pi thirds k. Now we're not looking for all solutions, but we are looking for the smallest 3. So that's going to be useful because right now, as you can see, I currently have all of 2 solutions. So I will need to use that plus 2 pi thirds k to generate a third solution. Now back over here, when we divide by 3, I'll just take this rounded value. I think that's good enough. 5.560451. I definitely went out a good number of decimal places. That's why I feel good about using the rounded value. And that is going to be that x is equal to 1.85, we'll say 35, plus 2 pi thirds k. Okay, so now I have 2 solutions, the 0.2409 and the 1.8535, and I have a way to generate additional solutions. So my smallest, here's my first smallest, 0.2409. My next smallest would be 1.8535. And then my next smallest would be what happens if I go around the circle again. So I'm going to take the 0.2409 and add 2 pi thirds, 1 copy of 2 pi thirds. So take the 0.2409 and add to that 2 pi thirds, and I have now 2.3353. And going back to my open math, moment of truth. Here's the 0.2409 that I listed on the board as the first solution, right there. Then the next one was 1.8535, so let's see that listed now, 1.8535. This says at least 2 decimal places, so by going out 4 decimal places, I was definitely on track. And then here's the 2.3353 that I generated, 2.3353. I generated this one, remember, by taking the 0.2409 and adding the first multiple of 2 pi thirds k would be just 2 pi thirds. So I added 2 pi thirds onto this number, and voila, I get my third value. And those are the 3 smallest values. So there you go. All right, back to my open math again. Okay, question number 8. Tangent is already isolated, so first question, where is tangent equal to 0? Tangent is equal to 0 on the unit circle wherever sine is equal to 0, because tangent is equal to what? Sine over cosine. So wherever sine is equal to 0, tangent is equal to 0. So we're looking at 0 and pi. In particular, we're looking at 0, come on, give me a 0, plus all multiples of pi. Remember that with tangent and cotangent, they have a period of pi, so you're going to have your value repeat itself every pi k as opposed to every 2 pi k. And it would be pretty silly of me to write 0 plus pi k and then also write pi plus pi k. So this is a lot more efficient. We just have one initial solution here, and that is 0 plus pi k. So once you set 4x equal to 0 plus pi k, then of course you want to divide everything by 4. And then the question of the day is, can you count by 1/4? 1/4 by fourths? How do you say that? By fourths. 1/4, 2/4, 3/4, 4/4, 5/4, 6/4, 7/4, 8/4. Ah, when you get to 8/4, that's 2. Look at your solutions. 0, 1/4 pi, 2/4 pi, 3/4 pi, 4 force pi, 5 force pi, 6 force pi, 7 force pi. Ta-da! Okay, number 9. So in order to solve a cotangent problem like this, I would rewrite this as a tangent problem. That is, if that's how you prefer to do it. I'm going to actually back up on that. I don't want to write that as a tangent. I would do that if I were dealing with an arc cotangent. I would rewrite that, but I'm not going to. Instead, what I want to think of is that cotangent is cosine over sine. So we need some sort of cosine over sine ratio that is going to equal negative root 3. Okay, so I want to make this clear. This is not my work. This is what's going on in my head. That's me. This is me thinking. Okay, so cotangent, I know, is cosine over sine. Now, I need somehow to get a cotangent to have an output of negative root 3. How do I get a negative root 3? 2 ways. I either have a square root of 3 over 2 divided by a negative 1/2, or I have a negative square root of 3 over 2 divided by a positive 1/2, right? So those are the 2 different possible ways I'm getting a cotangent value of negative root 3. So this is how I come up with cotangent values in my head. I just break it into cosine over sine, and then I think about on the unit circle, there are only so many numbers to work with. Which of those number combinations would result in a cotangent value of negative root 3? So now, on to drawing the unit circle. So where do we have a cosine of root 3 over 2 and a sine value of negative 1/2? It would be at this point right here, which is a 11 pi over 6. And then the other question is, where do we have a cosine of negative root 3 over 2 and a sine value of 1/2? And that would, of course, be pi away from my other answer. Remember that tangent and cotangent have a period of pi, so you're going to see these values repeat every pi, right? Every pi, the values keep repeating because tangent and cotangent have a period of pi. Okay, so now I have these 2 initial values that I'm going to now set equal to 3 theta over 2. Let me do this on the board. Okay, I'm trying to figure out how to get back to the board. One moment. It turns out to get back to the board, I had to erase everything I did on my open math. So I cannot refer back to it, but you can in your video. So now 3 theta over 2 is equal to 5 pi 6 plus pi k. There's no need to also list 11 pi 6 because that value is pi k away from 5 pi 6. So now we just need to divide both sides by 3/2, which of course would be the same thing as multiplying both sides by 2/3, and the result is that theta is equal to 10 over 18, which is 5 pi 9ths plus 2 pi 3rds k. Now, when you're actually generating solutions, you might find this helpful to think as this is a 5 pi 9ths plus 6 pi 9ths. It's a lot easier to add fractions with a common denominator, right? So I just rewrote 2 pi over 3 as 6 pi over 9. So I just need to add 6 9ths onto 5 9ths. So if you're generating a whole lot of the values, you would start with your 5 pi 9ths. Then your next value would be adding 6 onto 5, which would be 11 pi 9ths. And then your next value, you add another 6, so you get 17 pi over 9ths. You see, you just keep adding 6 to the numerator. So 5 plus 6 is 11, 11 plus 6 is 17, then you have 23 pi 9ths. How far do I need to go? Well, let's look at the directions. The directions say that I need to go all the way up to 2 pi. Well, 2 pi is going to be 18 pi over 9, right? 18 over 9 is 2, so we would only want to keep these first 3. By the time you get to 23 pi over 9, you've gone past 2 pi. So going back to the computer here, you can see my solution set: 5 pi ninths, 11 pi ninths, 17 pi ninths. Okay, I think you can do question 10. It's the same concept, except that secant, remember, has a period of 2 pi, so you will need to have 2 different sets of solutions there. All right, this is good times. Question number 11. Give the general solution for the following trigonometric equation. Rewrite, and it is an equation with a single function of a single angle. So what you want to do is you want to go to the back of the book and say, where do I see cosine, cosine plus sine, sine in my formulas? And I see cosine, cosine plus sine, sine in the sum and difference identities. That would be cosine of a minus b. So cosine of a minus b gives you cosine a, cosine b plus sine a, sine b. So we're looking at a cosine of a minus b, where a is 3 theta and b is 2 theta. So really this entire left side could be rewritten as cosine of 3 theta minus 2 theta, and then that's equal to negative 1/2. Now, I don't know if the answer wants me to write cosine of 3 theta minus 2 theta or just simply cosine of theta. So let us look. What does the answer want? Just a plain old cosine of theta. So go ahead and do that subtraction. 3 theta minus 2 theta. Okay, now what are the 2 possible angles on 0 to 360? So we're going back to degrees here. And that would, of course, be 120 and 240. So that theta is equal to 120 plus 360k and 240 plus 360k. So the only difference here, instead of adding 2 pi k, we add 360 degrees k. The degree mark is already part of the answer here, so you don't have to add the degree mark. If you were doing this by hand, you would include a degree symbol here. All right, so this problem is just in degrees, but this part here looks intimidating. It's really not. Just look at the back of the book at the sum and difference identities. So now that you are all geared up for sum and difference identities, let's come to question number 12. I'll do this one on the board. So for question 12, I want to start at the back of the book and look for sine cos minus cos sine, and I see sine cos minus cos sine in the sine a minus b. So that means that I have sine a minus b is equal to negative 0.25. And now I can rewrite this, of course, as the sine of negative 2x. Now you can proceed from here, but you can also just remember this, that sine is an odd function, right? So that the negative inside has to pop out. So we end up with negative sine of 2x is equal to negative 0.25. So if this had been cosine, cosine is even, so you would not pop the negative out. Tangent's odd, odd functions get the negative to pop out. So this is then sine of 2x is equal to positive 1/4. So on the unit circle, I've got 2 values here. The calculator is only going to give me the one that's in the first quadrant, right, because of the sine inverse moon. So I go back to the graphing calculator, or not the graphing calculator, the scientific calculator, and I want to do the sine inverse of 1/4. And I end up with 0.25268. So to get the other dot on the other side, I need to take 2 pi, not 2 pi, pi, here's pi. Take pi and subtract from pi that same little tiny angle. We are in radians, I checked. Okay, so take pi, well, I'm just going to subtract pi from this number, and then take the opposite, hopefully. Oh, no, not in parentheses. That's not what I meant. Close the parentheses first, then subtract the pi. So really, I want pi minus arc sine of 0.25. But I'm doing the opposite and then dropping the negative. Hopefully you tracked with me. Okay, so the second dot is going to be 2.8889. Going back to the problem, what am I actually doing? The smallest two positive solutions. Okay, so, oh, they didn't give me the smallest. Oh, there is no 2. I don't know why I'm reading a 2. It's just the smallest positive solution. I only needed 1. Okay, so going back then, I did not even need this second one. I did that just for fun, evidently. Normally, of course, that would be plus 2 pi k, and then this one would be plus 2 pi k. But in this particular problem, we only need to find the smallest. So we just take the 0.25268, set it equal to 2x, divide that number by 2. And what is this number when you divide it by 2? The number we saw on My Open Math, which is 0.1263, yada, yada, yada. All right, so that's it for My Open Math. I want to do one more problem on the board, and that is a problem from the textbook. Okay, number 62. Average monthly temperature in Phoenix. The following function approximates the average monthly temperature, Y in degrees Fahrenheit, in Phoenix, Arizona. Here, X represents the month, where X equals 1 corresponds to January, X equals 2 corresponds to February, and so on. When is the average monthly temperature? 70.5. That's not a very interesting question. So I'm going to do 55 degrees. If you do 70.5, it's a slightly interesting. Okay, I'll do both. A is 70.5. When do we have 70.5? So we're going to replace the function with 70.5 degrees. We don't really need to use the degree symbol. We're in the middle of an equation. What's going to happen is that we are going to then subtract 70.5 from both sides and get a 0 on the left-hand side. And then when you have a 0 on the left-hand side, when you divide both sides by 19.5, the left will still be 0. So we end up with 0 is equal to the cosine of pi 6 x minus 7. So now what we want to do is say, where is cosine equal to 0? Cosine is equal to 0 at pi halves plus 2 pi k, and also at 3 pi halves plus 2 pi k. But as it turns out, these values are pi away from each other, so you could actually consolidate this. This is a unique situation with cosine and sine. They have their values of 0 exactly pi apart from each other. And so you could actually consolidate all this into just saying that at pi halves plus pi k, you're going to have a value of 0. So we're going to set the angle. Here's the angle. The angle is pi 6 times x minus 7. So we put that right in here. Pi 6 x minus 7. Now, the problem says when is it equal to 70.5? And we're going to have two different times of the month, because the whole, I don't know if you ever look at graphs of weather on weather.com or these other sites. I think it's kind of fun. But you can follow the average highs and lows for a whole year, and they turn out to be a sinusoidal function. And so it's pretty cool to see when you have your low, and then you come up to your average temperature. And so this is actually the midline, right? 70.5 is the midline of the function. So we're going to see it's going to be probably the spring and the fall, right? Because you're going to have that average temperature right there in the middle. Okay, so now we're going to divide both sides by pi sixths. Which is the same thing as multiplying by 6 over pi. So that would be 3. If I multiply this one, here, let me do it this way. Multiplying by 6 over pi. Okay, so that is going to be 3 plus 6k, right, is equal to x minus 7. So now we need to add 7. So when you add 7, you end up with x is equal to 10 plus 6k. You don't add a 7 to the 6k. Now if you're multiplying both sides by a number, it would apply to both the constant and the linear term. But when you're adding, you're only going to collect like terms. So what you want to do are find the numbers that are 6k away from 10. Now in a year that goes up to 12 months, you don't want to add 6 onto 10 because then you're at 16 months, which is more than the 12 months in a year. But you can subtract 6 from 10 and get back to 4, right? So that means that my two answers for the year are x is equal to 4 and x is equal to 10, which corresponds to April and October. So that would be for part A. Now I'm going to go through here and we'll do part B. I'll just erase different parts here or there. So for part B, we're going to be looking at when we get to 55 degrees. So for 55 degrees, we're going to replace f of x here with 55. And then when you subtract 70.5 from 55, so let me go back over here to, I'm going to take 55 and I'm going to subtract 70.5. And I get negative 15.5. And then I need to divide that number by the 19.5 that's out in front of the cosine function. And I get this number that I'm going to have a long decimal approximation for, which is negative 0.7948. 7, yada, yada, yada. Okay, now this number right here is actually representing a number on the unit circle. So I would want to draw a picture of the unit circle and take the arc cosine of that answer. So here's the answer button. So I'm going to do arc cosine of that last answer. Isn't that handy? And I end up with 2.4859. I think that's enough decimal places. So I wrote that right here. So here's the first location. And then the other location where you have a value of negative 0.7948 will be right on the other side of pi. So these two angles being identical, we can find this other one by taking 2 pi and subtract from 2 pi. This would be 2 pi minus 2.48959. So I'll just go back now to the calculator and I'll just take this number right here and I'll actually subtract 2 pi from it. No, not inside. Close the parentheses. Minus 2 pi, and I end up with, I'm going to take the opposite because I did it backwards, 79359. Okay, so what I want to do now is take these two values right here and set them equal to what's on the inside here. So we have pi 6 x minus 7 is equal to 2.48959 plus 2 pi k, and then also pi 6 times x minus 7 is also equal to 3.79359 plus 2 pi k. And now I want to multiply both sides by 6 over pi, as we did last time. Okay, so that is going to give us then that x minus 7 is equal to, goodness, let me take this number here back to the scientific calculator here. I'm going to take 2.48959 and multiply that number by 6 divided by pi. And I end up with 4.7548 plus 12k. Right, because if you multiply 2 pi k by 6 over pi, the pi's cancel, giving you just plus 12k. Last time we had plus 6k because the values were exactly pi apart from each other. This time we're doing values that are 2 pi apart from each other, and we have two different sets of values here. So then we have x minus 7 is equal to, and now we're going to take this value right here. All right, so clear. 3.79359 multiply by 6 and divide by pi, and I end up with 7.2452 plus 12k. Almost done. Very close to the end here. Okay, so now we just have to add 7 onto these values. Let me erase up here. Okay, if you add 7, we have x is equal to 11.75. I'm going to keep that number because I could add plus 12k, but this number right here is like, what, close to December? 11.75, 3/4 of the way through November. This one right here, x is equal to 14.2452 plus 12k. I actually want to subtract 12 from that because 14 exceeds my year. So then I'm going to get 2.25 as my other answer. So a little into February. February, about a fourth of the, I don't know exactly how the months are. Yeah, so the answers in the book says during February and during November, right? So here you have November, and here you have February, based off those values right there. Whew, okay, so we are solving equations. Yay, hopefully you are enjoying that. And then after this, I think we only have the test. We are done with Chapter 6. So exciting. The next video I will be posting, I'll actually have 2 videos per test review so that you can be super prepared for the next test, which I hope you will do awesome on. Okay, have a great day and keep up the hard work.